Good morning, my name is Nicolas Huybrechts. I'm a researcher from Cerema in France, and today I will present you an application of the subnet technology inside the Bay of Oti. The Bay of Oti is located near Berck-sur-Mer, which is a city in the north of France. So the estuary of the Oti is characterized by the large percentage of intertidal area, and between this intertidal area, the river is flowing. This river generally meander and it regularly threatens the right bank of the dune and the shoreline. So the last severe erosion occurred in 2011 and 2018. So the meander approach and erode the dune near the shoreline. This dune presents a natural coastal defense for the hinterland, and this hinterland is lower the mean sea level. So the city hall, they installed big bag in geotextile on the top of the dune to control the flood risk. However, up to now there's no solution to control the risk of erosion of the shoreline. The situation we want to avoid is the one you can see on the figure, where the river is very near the shoreline and it can erode the dune. So this figure is looking to the land. This figure is the same as looking to the sea, and there you can see that the river is very close to the shoreline and the top of the dune. The solution we have tested on this Endure project is the subnet technology. So it consists of fishing net, but compared to the fishing net, we are stretching the net in order to reduce the void and to have a high porosity. So it can be about 10 or 20% of porosity. The net are assembled in different layers, about 4 or 5 layers of net. And these layers are lying on the sandbank at low tide, and during the high tide, they are raised by the buoys, and during the high tide, the net looks like a teepee, and the current are crossing this different layer of the net, and they are losing the energy, and then we are expecting to have sedimentation around this device. In 2014, we installed a first device in the Bay of Oti. It is represented by the white line on the picture on the right. On this picture, you can see the north shoreline we want to protect, the Fair Road. And you can also see a large sandbank. This sandbank is growing and then is pushing the river to the north, and the river then can erode the northern shoreline. So we raised the device 2 times, in 2017 and 2016, and finally the device was destroyed by a piece of wood. So during the Endure project, we have installed a new device which is located just after the white line. So it will be more in the north. The net has been installed on March 2019. So you can see the installation. We put the sand net first on the sandbank, and then we progressively enter the riverbed. up to 1 meter, as you can see on with the wheel of the truck. And then on the last figure below, you can see the net after the installation. So it looks like a grown, but it is grown which is porous. After the installation, we perform monitoring with different topographic survey with a flying drone, and we have also performed bathymetric survey around the net device and inside the bay. Tide and velocity current have been also monitored. On the black line, on the figure on the right, correspond to the area covered by the flying drone, and the red area correspond to the location of the bathymetry survey, which are more local. Now I will present you the result of the in-situ survey. So you have three figures on the bottom corresponding to three different surveys. The first one was conducted in March 2019, few days before the net installation. So the net device is represented by a black line. You can see on the first figure on the left that the net is inside the white area, which corresponds to the riverbed. And then you can see on the left a red area, which corresponds to the sand pit, and on the right it corresponds to the shoreline we want to protect. In the middle figure is the configuration after a few months after the installation of the net device, and you can see around the black line some sedimentation. And we can also notice that the river width has decreased just in front of the net device. If we look to the configuration in September, we still have sedimentation around the net, and we see that the river width has been stabilized. But one drawback of this topographic survey is that we do not have data inside the riverbed, so we complete the dataset with some bathymetry. On this slide, you can see two bed evolution, which have been measured between February and April, and between April and July. So the one on the left corresponds to a mixed configuration when we have installed the net of end of March. So we have about 1 month and a half with without the net device, and then we have a few days with the net. On the right, we have more configuration where the net was there all the time. So about 2.5 months with the net. So we can see on the figure on the right that near the black line we have some deposition, sedimentation, and then on the left you see some blue area which correspond to erosion. So we have analyzed the bathymetric evolution with a transect, a profile taken from the left to the right. So the 0 corresponds to on the sand spit, then we cross the river, the sand net device, and then we go until the shoreline. So on the figure on the right, we see the profile, the bed profile for the two surveys, the one in April and the one in July. So we see that on the left, compared to the location of the net, so the net are about 100 meters from the sand spit. So on the left, we notice some erosion, and on the net and nearby the net, we see some deposition. Here's the comparison between July and September, so until 6 months after the installation of the SUNNet device, and we see that the configuration is stabilized. We see that in the purple line that the rivers still continue to deepen its channel, and we still have more deposition sedimentation across the SUNNet device. If we compare the two bathymetry survey, which has been measured by the City Hall, we see that in February and in October, so the white line is the SUNNet device, and the yellow line corresponds to the main channel, the deepest area of the channel. So we see that in October, the main channel has moved to the west part of to the west compared to the SUNNet device. Means that the east part there are more sedimentation, and this part looks to be protected by the SUNNet device. To go further in the analysis, we have built a numerical model with a Telemag 2D, and we couple Telemag with the sediment transport module Gaia. For this model, we consider short time scale, it means a few months, and we only consider the tide and the flow rate. The model has been calibrated with the different in situ data we have, so mainly tide and tidal current, and we implement the net inside the numerical model through an additional drag force. And then we want to see the effect of this drag force on the sedimentation. But to do this, we need to specify a value for this drag coefficient, which is in fact unknown. To determine the value of this drag coefficient, we conduct some frame experiment inside the experimental flume at Ifremer. So in this experimental flume, we use a device which is similar to the one we have in the Bay of Oti in terms of width and height. And in this flume, we need to maintain a constant water level at 2 meters, and then we can impose different velocity upstream. Then we perform different velocity measurement, and what we can see, you have here the purple line, the profile, which is taken upstream the SUNNet device. And for this profile, the velocity is quite uniform. And then you can see the profile in yellow and green. These profiles are taken just downstream the SUNNet device. And we can see two layers flow. Above the SUNNet device, we have an increase of the velocity up to 1.6 meters per second. And then on the lower part, we see that we have a velocity decrease up to 0.3. So as the sediment transport generally happens near the bed, we expect that this velocity decrease will be associated to a sediment trap. Then we have also a measurement of the force acting of the SUNNet device, and we were able to determine the drag force coefficient, which is equal for this flow configuration to 3. But this value of the drag force coefficient is valid for the water level of 2 meters. In the OT estuary, we have the tide influence, and then we have different water depth. So we want to determine how this drag coefficient can be modified by the tidal influence. As we cannot modify the water depth inside the experimental flume, we conduct numerical experiment using a 3D numerical model, Telemac 3D, and we represent the SANnet through a bathymetric step. So you can see that we can model different water depth, and then we can extract the energy losses for the different configurations, and then we can determine a relationship between the drag coefficient and the ratio between the water depth. So we compare the water depth upstream the device and the water depth on the top of the device. So the flume configuration we study at Ifremer, we have a ratio about 2 meters. So on the top of the device is twice the upstream water depth, and we have a drag coefficient of 3, and we see if we decrease the water depth, then it tends to increase the drag coefficient. And in opposition, if we increase the water depth, the bathymetric step has less influence on the flow, then we have less energy losses. Once we have this drag force coefficient, we enter the value inside a numerical model, and we let the model run for more than one month. So on the figure on the left, we have the natural evolution without the SANnet device, and then we have imposed two values of the drag coefficient, 15 and 13, and then we can see some deposit sedimentation near the net, the black area. And then we can also notice that with this SANnet device, we have more erosion in the area between the sand spit and the net. So it looks like the river is blocked by the sand spit and the SANnet device. If we look to a transect, we can compare that situation. The blue line is the natural evolution, so we will have more sedimentation erosion near the net, and if with the SANnet device, we can see that we have sedimentation. So the SANnet acts as a protection in this area, and we see also that on the left, the river is deepen this channel with the SANnet device. So to conclude, from the in situ experiment, we have observed sedimentation around the SANnet, and we have noticed also that the river has deepened this main channel. So it is the effect we were expect, but we see that due to its length, which is quite short, so 100 meters compared to the shoreline we want to protect, it has a local effect. So it's not sufficient to protect the whole shoreline. So we can see, for instance, on the satellite image, between February and September, that in the area where we have located the SANnet, it allowed to maintain the river on the left, on the west part, but then we see that the channel has a meander in the southern part. Then when from the observation, we see that we have an effect of the SANnet. We have sedimentation in the net. Then we conduct some flume experiment and numerical experiment to better point out what is the effect of the SANnet compared to the natural evolution. So we notice with these two kind of experiment that the SANnet has a real impact, and induce the effect we want to observe. But up to now, we have conducted experiment which is quite short, about a few months. We still need to analyze how it will behave for a longer time scale when we have the storm. So thank you for your attention. See if you have some questions.